Thank you so much for coming to Flight and coming to this talk about scaling the answers backend. My name is Solovey, and I'm an engineer on the answers team. So before we dive into some of the challenges that we faced on answers in the last year and a half, let's talk about what answers is. So answers is the mobile analytics part of the Fabric Developer Suite, and there are a lot of other mobile analytics solutions out there. What makes answers unique? So since day one of developing answers, we wanted to be real-time and opinionated. We wanted every number in our dashboard to tick all the time and to give you the latest value for that metric. We wanted to be opinionated in comparison to our competitors that kind of overwhelm you with a bunch of data and request the end users to sift through that data and decide which of that data is meaningful and actionable. So here's a look into our dashboard. And as I said, everything ticks in real time. And front and center, we've chosen 6 metrics that we believe are important to every single mobile application out there. Those metrics are daily active users, daily new users, monthly active users, crash-free users, sessions, and session length. And right below the metric, we give you some context into that value. We show you the delta of the metric right now to the same exact minute of the day a week ago. So we're giving you a week-over-week context down to the minute granularity of the day. And as you see in this snapshot, daily new users is highlighted because it's 11% higher than it was a week ago at this minute. So we're kind of encouraging you and drawing you to look at that metric, click into it, and dive in deeper to see why that metric is higher than it was a week ago. As I'll be talking about scaling answers, I'll be talking a lot about events. And the Answers SDK in the product is built on top of events. So every application out there that has answers enabled is constantly collecting events as users are using those applications, recording those events, and then periodically flushing those events to our backend servers. Just to give you an idea what some of those events are, every time someone installs an app that has answers enabled, we record an install event. Every time an app goes into the foreground or background, we record those events. And then on the back end, we can take those foreground and background events and stitch together notions of user sessions. So we can see when someone has the app in the foreground and is engaging actively with the application. Our crash event allows us to give you the notion of stability. We can compare the active users versus the impacted users. And just a few months ago, we released a feature called Answers Events. And that's where predefined events and custom events come into play. All the other events are useful for every single application. But Answers Events allow the developers to tell us what's unique about their application. So you can tell us events that you otherwise wouldn't know to record. Since this conference last year, the number of applications using Answers has grown by over 3 times. So we're obviously thrilled by this growth, but at the same time, that presents scaling challenges for us. Similarly, if you measure the growth in the number of events that we process, we currently process 1.5 million events every second. So just in the few minutes that I've been talking to you, our backends have processed hundreds of millions of events. And again, this is super exciting for us because of the wide adoption of Answers, but it's challenging for us to be able to scale to handle that kind of growth. So before diving into our scaling challenges, just a quick overview of our architecture to give you kind of the context. For processing answers data, we use an architecture called the Lambda architecture. And the idea behind the Lambda architecture is that ideally, when you have all this information coming into your system, you process it offline. You take a finite set of the information that came in, usually maybe a day's worth of events, and you run it through a MapReduce framework, and you get insights into the data that way. And the benefit of kind of the batch or offline layer is that the computations are repeatable and they're durable. If machines crash when you're performing these computations, that's not a problem. You can just start the computation over again, and you'll get the same values back. So that's really nice. Kind of the limitation of the offline layer is that it's not real time. You could build an analytics product simply with an offline batch layer, and it'll give you nice, accurate results. But those results will either be hours or more likely days stale. So to compensate for that, the Lambda architecture calls for having a parallel, real-time, or speed layer. And the idea behind the real-time layer is that in addition to processing all the information offline, you perform the exact same computations in real time. So you take the events, you split them, you make 2 copies of them, you save them, save 1 copy for offline processing, and process this constant stream of 1.5 million events per second in real time. So in today's talk, I'll focus on the real-time layer. Because of this influx of data, this stream of data going through the real-time layer, it kind of presents slightly more interesting challenges. When machines go down in the real-time layer, when they come back up, it's not clear how much information they've missed. So there's some really interesting problems with scaling the real-time layer. But before talking about the challenges that we face scaling the real-time layer, let's talk about kind of the ideal scaling scenario for any distributed system. So let's say we have a distributed system that's made out of 4 machines, and those machines process 1.5 million events in a day. And the output of those machines is this nice dashboard. Ideally, as events come into the system, we could send those events arbitrarily to any machine. So for example, if we were to get an event for the Cannonball app, we can send it to any machine in the cluster. If the next event happened to be for the Twitter app, we could send that to any machine in the cluster. And then if another event came in for the Cannonball app, if you know the first event went to the machine on the right, ideally, we can just send this event to any other machine. And so in this case, we would send it to the machine on the left. And kind of spreading the events equally and arbitrarily across the cluster means that each machine is roughly processing the same amount of work. And what that does is it allows you to scale your system linearly. So let's say that we came into the office on day 2, and now we saw that our framework was more popular. We have to process 1.25 million of events on day 2. If our system was nicely distributed and load was evenly distributed across machines, to process that extra 250,000 events, we would just add another machine to the system. On day 1, each machine was processing 250,000 events. We would add another machine. It would take on 250,000 of events load, and we would get nice linear benefit in adding that machine. So we'd be able to scale. So that's ideal. In practice, things make this ideal hard to achieve. So let's dive into some things that made this hard to achieve for us. So let's talk about some of the computations that I showed you in our dashboard. Daily active users, which was front and center in our dashboard, is at its heart a cardinality computation. We want to tell you how many devices use your application on a given day. And if you were to approach this in the most direct way, in the most brute force way, you would keep a set in memory for each application. And as you saw events for each one of those applications, you would add those device IDs to the set that corresponded to that application. And you can imagine adding these device IDs to that set throughout the entire day in real time. And then to measure daily active users, to measure the cardinality, you just take the cardinality of that set that you're maintaining. This sounds nice. The problem is that we have applications that have millions and even tens of millions of active users on a given day, and the sets for these applications would simply grow to be too big. A set to keep track of tens of millions of active users would be 100 megabytes, maybe even gigabytes in size. And so that set would simply not fit on a single machine, or even if it did fit on a single machine, that machine would pretty much be dedicated to holding a single set for one application. And obviously, this would not be a cost-effective way for us to scale. Let's look at retention. We have a very similar problem there. Retention is our metric of how engaging your application is, how sticky it is for your users. So the idea behind retention is that we take the set of users who installed your application 30, 7, and 1 days ago, so 3 different sets of users, and today, as we look for activity in your users, we see which one of those users came back and used your app again today. So the higher your retention, the more sticky your app is. The more likely it is that people who installed your app some time ago are actually still using it today. So if you think about the most straightforward way to perform this computation, you need to have 3 sets. You need to have a set for the folks who installed your app 30 days ago, 7 days ago, and 1 day ago. And then as activity came in, you would compare the device IDs to those 3 sets. And again, same problem. We have applications that are super high volume. Millions of users install those applications on a given day, and these 3 sets would look very, very large in size, and they wouldn't fit on a single box. Lastly, session duration. We show you median session duration in our dashboard front and center. To compute this in the most straightforward way, you would maintain a sorted list of session durations that you've seen on a given day. And as new session durations came in, you would add them to the sorted list, make sure it's still sorted. And to find the median, you would just take the length of the list and find the session duration that's in the middle of the list. Sounds nice in theory. In practice, we have apps that have tens of millions and even hundreds of millions of sessions in a given day. So this nice sorted list would go really large in size again. It would take hundreds of megabytes, maybe even a gigabyte to store. So to address this kind of space problem, to address the problem of the amount of space we would need for all these data structures, we use something called probabilistic data structures. And probabilistic data structures allow you to make a very small trade-off in accuracy loss for a huge gain in either time or space complexity. And in our case, we're interested in space complexity here. So let's look at daily active users again. there's a probabilistic algorithm called a hyperloglog, which allows us to perform the same daily active users computation while using 1,000th of the space. So we sacrifice less than 1% error loss, but we gain back 1,000 times of space. And I'm not going to go into detail into these probabilistic data structures, but there's plenty of literature about them online, and I encourage you to read up about them. Hyperloglog is a particularly beautiful algorithm, so it's very interesting to read up on. For retention, there's a probabilistic algorithm called a Bloom filter. And a Bloom filter tells you at a device level, at an individual set member level, whether that set member is in the set or not. So it's perfect for our retention computation. You can have a Bloom filter for the D30, D7, and D1 retention computation. And as we get activity, we just offer it to the Bloom filter, and we can compute retention that way. We get 100 times space gain from using the Bloom filters. And if you note, the space gain here is slightly smaller than in the case of the hyperloglog. And that's because Bloom filters give you a more granular answer. You're asking a much more granular question. You're saying, is this member in this set? And getting an answer at the granularity of a single set member. For median session duration, we use an algorithm that's homegrown. And I'll go into detail on this one in more detail because there's not literature about this one online. And similarly, in this case, we get a 500 times space benefit, again, at the cost of less than 1% error loss. So let's talk about how we compute median session duration. So let's go back to the brute force method of computing median session duration, which would have you maintaining the sorted list of session durations. And you can imagine an application that has these session durations. And in this case, we have granularity down to the milliseconds. So basically, the space of potential session durations is pretty much infinite when you have a lot of granularity like this. So the accuracy trade-off that we make here is to round down the session durations to the nearest second. So we represent them like this, just getting rid of the millisecond granularity. And what that allows us to do is to represent the distribution of session durations for an application via a bunch of counters. So for every second between 0 minutes and 10 minutes, which is 600 possible seconds, we have a counter that counts how many sessions we've seen at that duration. For every session between 10 minutes and an entire day, we have counters at the minute level. The reason that we have more granularity between 0 and 10 minutes is because most of mobile app sessions are in the 0 to 10 minute range. There's way fewer mobile app sessions that last over 10 minutes. So the distribution on that end is much more sparse, and we can get away with having less counters there. So basically, with slightly over 2,000 counters, we're able to count all the session durations that we've seen for an application over the course of a day. And we don't have to store this potentially infinitely long list. So let's go into more detail about how this works. So if you think about these counters, they kind of look like a histogram. So let's say you have an application that's seen 25 sessions today. And this histogram tells us that we've seen one session that's been 1 second long, 3 sessions that were 2 seconds long, and so on. And as new sessions come in for this application, all we have to do is find the counter that represents the session duration and increment it by 1. So if we saw a session that were 5 seconds long, we'd find that counter and increment it. If the next session were 8 seconds long, we'd find that counter and increment it, and so on. And we keep doing this. And if you note, there's a big difference between the cost of this operation versus the cost of updating a sorted list. In this case, this operation is constant in time with respect to the number of sessions that we've seen, because the number of buckets, the number of total buckets that we're maintaining, is at most 2,000. So the number of buckets is constant, regardless of whether we've seen 1 million or 10 million or 100 million sessions. And we keep doing this. We keep incrementing counters. And let's see if we get to 30 sessions for this application. So how do we find the median session duration using this data structure? So at its heart, this data structure is just a sorted list of session durations. So we know we've seen 30. We want to find the 15th session duration, because that will be the median. So to find the 15th session, we basically start counting from the left, and we just have an aggregate rolling counter. So we know that there have been 4 sessions that are 2 seconds or shorter. And if we keep counting, we're looking for the 15th session. We know that 7 sessions are 4 seconds or shorter. If we keep going until we get to this bucket that has that's 7 seconds long. So now there are 15 sessions to the left of that bucket. So we know that median session duration is 7 seconds long. And if you note, even this operation of actually finding the median session duration is also constant in time with respect to the number of sessions that we've seen, because we're traversing at most a constant number of buckets. So regardless of how many sessions we've seen, this is a constant time operation. So this saves us a lot of space and a lot of time as well in performing these computations. All right, so probabilistic algorithms are nice. They help us address the space complexity, but they actually introduce new complexity into our system. If you think about them, it's easiest to reason about them if you have the guarantee, the constraint, that there's only one of these probabilistic data structures for each application. It's easiest to think about a single hyperlog log for an application, and a single Bloom filter, and a single histogram for session duration. It's not immediately clear what we would do if we, instead of having one hyperlog log for an application, we'd have many hyperlog logs. The problem there is that if we want to enforce this constraint of having a single data structure for each application, we can no longer spread our events across the cluster in an arbitrary manner, as was one of our criteria for the ideal linear scaling scenario. We have to ensure that every event for a particular application goes to the same machine, because that's the machine that's going to be holding these probabilistic data structures for that application. And at this point, there's a trade-off that kind of exposes the art of scalability. There's no right one answer to this. So, some folks might want to choose to encounter the complexity of enforcing that every event for an application goes to the same machine. Some folks might want to encounter the complexity of merging all these probabilistic data structures together after sending all the events to separate machines. We chose to address the complexity of enforcing that all events go to the same machine because the simplicity of reasoning about a single data structure for each application was so appealing to us. But there is complexity there, so let's talk about how we address the complexity. So the complexity of enforcing that all events for an application go to the same machine is a very common problem in distributed computing, and it's known as the hotspotting problem. So the hotspotting problem occurs because as events come into the system, let's say we send the cannonball event to the machine on the right. When another event for that same application comes in, we have to send it to the same machine. And so immediately, this doesn't seem like a big problem. And if all applications that we saw had roughly the same number of events, this wouldn't be a big problem. If all applications were roughly the same size, then we could assign applications to machines evenly, and each machine would still see a roughly the same number of events. The problem is that this distribution isn't the reality. So in reality, if you kind of group the applications that we see into buckets by size, you'll see that most of our applications would fall into a smaller or medium-sized application, and a much smaller fraction of applications would fall into kind of the largest size of applications. But if you look at the number of events that those applications are sending us, that small number of large applications sends us a huge majority of our events. And this problem, this distribution, isn't specific to us. If you look at any of the app stores, if you look at the few top 100 apps in those app stores, those apps are responsible for the majority of mobile internet traffic and mobile usage in the world. So if you go back to the assignment of applications to machines in our cluster, and if we start with this most straightforward way of assigning applications to machines evenly, what you would get is a distribution that looks like this. So most of the boxes in your cluster would be happy, but a few boxes that got the biggest applications would be seeing disproportionately more traffic than all other boxes in your cluster. They would be seeing so much traffic that the network on those boxes would get saturated, and those boxes would be the hotspots in your system. And the reason that the hotspots are so bad is that as the input into your system grows, if you have a hotspot in your system, adding more boxes to your system no longer helps. It might help a little bit, but it doesn't help linearly anymore, because you're not pulling away enough load from these hotspotting boxes as you add more machines into your cluster. So to be able to scale linearly again, we have to solve the hotspotting problem. And we approach the hotspotting problem in two ways. The first way is stream size grouping, and the second way is sampling. And I'll talk in detail about both of these approaches. So the idea behind stream size grouping is that even though it's easiest to assign applications evenly to machines, what we really want is to assign events evenly to machines, not applications. So we want to start with a distribution that looks like this, where the bottom two machines are hotspotting, and kind of move it towards a distribution that looks more like this, where we take the traffic away from the machines that are hotspotting and move them off to the machines that are not hotspotting, and move towards a more even distribution with respect to the number of events and not the number of applications. And the way that we do this is we look at the number of events that each application sent us on the day before, And we kind of make the assignment of applications to machines in a way that targets an even distribution of events. And this is easy enough to do. We can perform a bin packing problem and basically come up with an assignment of applications to machines such that the number of events that each machine sees is basically the same. And this is nice because now we're back at having an even distribution of events to machines. And as we add more machines into our system, they'll be able to take proportionate load off of the existing machines, and we can grow our capacity again. So this helps, but there are cases where this isn't enough. We have applications that send us so much data that even a single application overwhelms a single machine. If we have applications that have tens of millions and hundreds of millions of active users, and if we send all the data for that application to a single machine, that application by itself will saturate the network on a single machine. We'll be back to the problem where we have a hotspot, and we can do nothing about this. We can't. Adding machines to the system will not help the system at all, because this one machine that's hotspotting is hotspotting because of a single application that's assigned to it. So the way that we address this problem is sampling. So for applications that are so large that they would overwhelm a network on a single machine, it's enough to process a fraction of the events for that application and still get a very accurate and meaningful signal and very accurate metrics. And I'm going to talk about how we do this in a way that doesn't sacrifice accuracy. Before I dig into that, it's worthwhile to note that for the majority of applications, and for most applications that you folks in this room will build, we will never have to sample. Sampling is enabled for 0.2% of our applications. So 99.8% of the applications that we see, we process 100% of the data. But obviously, it's still important for us to not introduce a significant error for the applications that we do sample. So how do we sample? Let's imagine an application that's very high volume and has this kind of distribution of devices in the wild. And let's say that each device is sending us roughly 10 events. And let's say that we've decided that it's enough to process 10% of the events for this huge application to get an accurate signal. One way that we could sample would look like this, where we kind of arbitrarily take 10% of the events that we see for this application and arbitrarily across all of the devices. And we don't sample this way, because the problem with sampling this way is that we would likely end up with one event for each of the devices out there. And if you recall the section about the types of events that we see, we get foreground and background events. And if we did this, it's very likely that we would lose kind of the matching foreground and background events. It would completely eliminate our ability to stitch together a notion of sessions on the back end. So instead of sampling like this, we sample like this. We take 100% of the events for 10% of the devices. So for that 10% of the devices that we're processing data for, we're processing it as accurately as ever. And we simply don't process any data for 90% of the devices for these huge, huge apps. So to kind of highlight what we do for sampling, it's enabled for 0.2% of the applications that we see. And this is enough to reduce the aggregate traffic and number of events into our system by about 80%. So it's a huge win for us at a very, very small margin of error for that 0.2% of applications that we sample for. Kind of the same as the probabilistic algorithms that I talked about before. Our goal with sampling was to limit the error for it to be lower than 1%. And that's what we achieved with the way that we set sampling up. And the way that we set sampling up is we took these large applications and we empirically performed the computations against their entire data set and against a sample of their data set, 10% constantly sampled against a constant set of devices. And what we found is that if an application reaches roughly 200 million events per day, 200 million events per day of events that we see for that application, we can start sampling for that application at 10%, and the error rate would be limited to 1%. It's also worthwhile to note that for either lower volume events or events that are particularly important, like install events and crash events, we don't have to sample those events at all. Even for the applications that sampling is enabled for, we don't sample those events because they're low volume enough that we can handle 100% of that load. So in summary, as you kind of scale a distributed system to the scale that we've scaled ours, even though ideally you're keeping complexity out of your system, inevitably complexity will creep into your system. And I hope that this talk has kind of introduced you to some of the complexity that might come into your system, and also taught you that ideally you can't keep all the complexity out, but the goal is to understand the complexity that's coming into your system and make trade-offs between the complexities that you're letting in, and pick the complexities that you want to focus on and solve. Thank you very much for coming to this talk. I love talking about this stuff. I'll be at the answers booth for the rest of the day and also at the happy hour, so please come find me and ask me any questions that you'd like. Thank you so much.